Today I am giving lecture on atomic spectroscopy. The science of atomic spectroscopy has yielded three technologies for analytical use, namely atomic emission, atomic absorption, and atomic fluorescence. In atomic spectroscopy, atoms have to be volatilized either in flame or electrothermally in an oven. In this state, the elements will readily emit or absorb monochromatic radiation at the appropriate wavelength. Usually, nebulizers or atomizers will be used to spray the standard or test solution into the flame through which light is passed. Alternatively, the light beam is passed in an oven through a cavity containing the vaporized material. The wavelengths emitted from excited atoms may be identified using a spectroscope, a spectrograph, or a direct reading spectrophotometer that uses human eye or photographic plate or photoelectric cell, respectively, as detector. Now, atomic emission theory, spectroscopy. In emission spectroscopy, a sample is excited by absorbing thermal or electrical energy, and the radiation emitted by the excited sample is studied for both qualitative and quantitative analysis. Most of the spectroscopic techniques are related to molecules, but emission spectroscopy is related to atoms. You must remember that here we are talking about atoms, not molecules. Therefore, this technique is used as a method of elemental metal analysis. With it, all metallic elements can be identified and quantitatively determined in a very low concentrations, as can the metalloids such as arsenic, silicon, selenium, etc. Solids, liquids, or gases can be analyzed quite easily by this method, but most of the samples are solids or evaporated solutions. Liquid samples are occasionally analyzed, whereas gaseous samples are rarely analyzed. If proper precautions are taken, the method can be used for quantitative analysis of about 70 elements at a concentration level as low as 1 parts per million. So here we are going to study the elemental metal analysis, which is coming out from the analysis of atom, not molecules. Both qualitative and quantitative analysis can be done. Now let us see how it is possible, or what is the principle. If an atom is in the ground state, its electrons are present in lowest permitted energy levels. When electric or thermal methods excite the atom, its electrons move from inner orbital to the outer orbital. The excited electrons rapidly emit a photon of energy and occupy the orbital with the lowest energy or ground state. That is, excited electrons then emit the energy and come back to their lowest or ground energy state after attaining certain amount of energy. The emitted radiation from excited atoms in the form of discrete spectral lines forms the basis of emission spectroscopy. Now let us see the instrumentation. In emission spectroscopy, the sample is excited by thermal or electrical methods, thus becomes the source of radiation. Then the radiation is passed through a monochromator to select the desired wavelength and finally passed onto the detector, which measures the radiation for qualitative analysis. The various individual components of the equipment are described below. Excitation sources. Excitation sources in emission spectroscopy are flame, direct or indirect current arc, and alternating current spark. Any excitation source used for emission spectroscopy must accomplish the following processes. Sample must be vaporized. It must be dissociated into atoms. The electrons in the atoms must be excited to higher energy levels above ground state. It should be capable of exciting atoms of all the elements of interest. It should provide sufficient line intensity so as to detect these lines within detection limit. It should provide reproducible excitation conditions from sample to sample. Flame is used for those molecules which do not require very high temperature for excitation and dissociation into atoms. Different flames having different temperatures used in emission spectroscopy are shown in the following table. Fuel, natural gas may be there, oxidant is air, and temperature is 70-100 degrees centigrade. Oxygen, for oxygen it is oxidant. For natural gas, temperature may rise up to 2700 degrees centigrade. In case of acetylene, it is 2200 degrees centigrade. It can be with oxygen. It can reach to 3200 with oxygen. For hydrogen and oxygen combustion, we get temperatures of about 2800. And again, if acetylene is used with nitrous oxide, then it will produce 3400 degrees temperature. Now, nebulizer. The nebulizer passes a stream of air over the capillary tube, whose other end dips into the solution under test. Again, nebulizer passes a stream of air over a capillary tube whose other end dips into the solution under test. Indirect injection systems, large droplets will not remain in the hottest part of the flame for long and hence are allowed to settle in a cloud chamber. Combustion of air and natural gas gives a temperature of 1500 degrees centigrade, which is adequate for sodium determination. Calcium is better analyzed at 2000 to 2500 degrees centigrade. Magnesium and iron require same temperature, and for their heating, air and acetylene gas mixture is used. Now, role of monochromators. In emission spectroscopy, both prism and grating monochromators are used. The function of monochromator is to separate various lines of a sample's emission spectrum. Out of many lines, we need to choose the emission spectrum coming out of sample, and for that prism or grating are used for as monochromators. Detectors. Two types of detectors are widely used: photomultipliers and photographic plates or films. For qualitative analytical studies, photographic plates or films are used, while photomultipliers are used for quantitative analysis. Emission spectra may be examined by means of an optical arrangement that will identify component frequencies and their intensities. This optical arrangement is known by several names. For example, it is termed as spectroscope if it involves a visual device, spectroscope if it is carrying a visible device. It is termed as a spectrograph if it records many wavelengths simultaneously on a photographic plate or film. It is termed as a spectrometer if it scans the spectrum. Except spectroscope, both spectrograph and spectrometer determine intensities also. The basic layout of atomic emission spectroscopy is given in the following figure. Multi-channel polychromators allow the emission of up to 6 elements at a time to be measured. So, 6 elements may be measured simultaneously. Air from the compressor. This part is nebulizer. From here, sample is coming out, and they are ejected from here. Air plus sample are ejected here into the flame, which atomizes the sample. So these atoms then firstly go to electrons of these atoms, firstly go to higher energy state, then they emit photon to come down to ground state, and this photon is released, which is then analyzed by monochromator, and then the signal is sent to detector. Detector here is photomultiplier tube, and then enhanced signal is read out. Nowadays it is read out by digital displays. So this is a figure showing components of atomic emission spectrometer. Now, applications of emission spectroscopy. Emission spectroscopy is used for elemental, qualitative, and quantitative analysis. But this provides very little direct information about molecular form of the sample. So we get the idea of element, but molecular form of the sample cannot be detected from this method. In order to perform qualitative analysis, the emission spectrum of the sample is recorded on a photographic plate or film. The emission lines are then identified by comparing them with the lines from the known sample. Standard samples are also used to recognize the element or a spectral line. Emission spectroscopy has been used in many fields to provide useful information. Iron and steel, as well as the aluminium industries, are based on emission spectroscopic analysis in all steps of their process. This is done to control the composition of molten metals before further processing. For example, the presence of nickel, chromium, silicon, manganese, molybdenum, copper, aluminium, arsenic, tin, cobalt, vanadium, lead, etc. In iron and steel, it has been determined on a routine basis by using automatic emission spectrograph. All these elements have been estimated in concentration ranges varying from 0.001% in iron to 30% in steels. Numerous elements can be determined simultaneously by this method with very little sample preparation, and it takes very less time also. It has also been used for analysis of aluminum alloys, magnesium alloys, zinc alloys, lead alloys, and tin alloys. Some of the trace elements such as vanadium, copper, nickel, and iron have been estimated by employing automatic emission spectrogram. It has been used for the analysis of many elements including sodium, potassium, zinc, copper, calcium, magnesium, nickel, iron present in tissues of human and animals also. Changes in trace metal concentration have been studied as related to aging process and also for the various deficiency diseases also. This is indicative of uh, the disease or malnutrition present. Emission spectroscopy has been used to detect elements in plants and soils. This has been done to diagnose deficiency problems in plants. So this was an introduction to emission spectroscopy.